Thank you. Thank you, Tom, for the invitation. Microphone on? Is it? Is it? Okay. All right. All right. Okay. Is this working? That's working. Okay. Great. So thank you for the opportunity to be here and to speak. And yeah, my name's Elliot Paquette, and I'm continuing with what we were doing. I've never given a joint talk with Courtney. I have no idea how long I budgeted, or we'll see. We'll see how this goes. So thanks for your patience. So I'm talking about yeah, joint work with Courtney and also Jeff Pennington and Ben Adlam, and also some of the authors that were presented in the previous part. Okay, so so a lot of what I'm going to do relates to the previous part. I'm going to here's the plan of what I'm going to say. First of all, I'm now going to talk about single batch SGD. So what you saw before was that the batch size was an important parameter. There's something that we're leaving out in the story about what happens for sort of intermediate size batches, which are vanishing as a fraction of the full size. We have some good evidence that it basically behaves like single batch SGD, for which reason I'm just talking about single batch SGD. So I've written it for you. So here's what the only algorithm that will appear in what I'm doing at this moment. It's just this iteration, and it's only going to be this problem. So minimizing 1/2 ax minus b squared, and I'm going to add a regularizer, which is common practice. And just to emphasize, this is SGD. So what's happening here? You're making a random choice of function. So we had a finite sum before. So the randomization here is that at the kth step, you choose a EIK, and IK is chosen uniformly at random from amongst all the n possible functions. And there's a great question about what to do if instead of choosing these uniformly at random, you do some single permutation and then run through it over and over again, which is closer to practice. But in any case, I'm talking about uniformly at random. So here's the plan. I'm going to do 3 things. So our analysis of this problem is based off of an idea of basically of comparing this discrete time process to a corresponding continuous time random process, and specifically diffusion. And so in this part of the talk, I'm gonna have Brownian motions, and I'm sorry if you don't like that. I'm gonna make them appear in this part, and then they're gonna go away. So bear with me, and there will be no more Brownian motion at some point. But I think it's an extremely helpful tool to understand this this process. The second thing is everything that I'm doing is inspired by random matrix theory, and there is some random matrix theory content here. I'm going to formulate a theorem that holds for deterministic A and B. And there's going to be some conditions on that A and B, which if you don't do random matrix theory, you're going to think look weird. But they're deterministic conditions. So there are principal non-random matrices to which what I'm doing applies. Okay, and then I'll talk about a deterministic analog and so forth. Okay, so let me start with this homogenization of SGD. What do I have to do? Go back and click your slide. We're going to click the slides. Okay. Okay. All right. So homogenization. So it's a very common approach. You'll see in literature about stochastic gradient descent to try to take the fact that it's a Markov chain and then make a comparison of what happens when you take a Markov chain which makes tiny steps and say that, well, if you have a Markov chain which makes a bunch of tiny steps, it starts to look like continuous time analog, which is a diffusion process. And it's basically a consequence of the central limit theorem that such a thing works. What you do is you take the increment of the update, compute its conditional mean, you compute its conditional covariance. The mean becomes, well, it's preserved. And the important simplification is that the increments, the random part of the updates, if they're all small, then the central limit theorem type behavior takes over and you see basically a Gaussian update. So you would have something like a small Gaussian update with some covariance matrix stuck in there. So if this is the mean term, then the type of behavior you would see if this and this interpolate some kind of continuous function is basically the random analog of an ODE appearing. So this X starts to behave like a continuous X hat. And let's suppose that you took your gamma K, my step size, and I'm going to allow them to change with K. But if you assume that they were interpolations of some smooth function, if your mean has a continuous type dependence and your correlation has a continuous type dependence, then you see in the end an ODE appearing. And this actually you can make good on this type of analysis, and people have done this for SGD actually in quite great generality. So there's a nice theory of goes by the name stochastic modified equations, where you take SGD in more generality that I'm presenting, and you basically do this computation, and then you try to make rigorous comparisons between the behavior of SGD and the corresponding SDEs. Now, in generality, the theory here, if you apply it to the situation that I'm talking about, would actually only apply in a very, very small window of time. So in such a short window of time that the algorithms haven't actually moved. So it doesn't give you very much. So we're going to do a more in-depth analysis of this particular case. And we need an extra idea. So part of the problem with using this idea for SGD is that you really need that these functions are nice, smooth functions. You kind of also need that the dimensionality of the problem is fixed, and our dimensionality is getting big. So second thing. So it reminds me of another phenomenon, which is called homogenization, which basically is the same idea as diffusion approximation, but it takes care of adds one extra idea, which is that if you actually compute this conditional mean and conditional covariance of SGD, you see something which is very rough. It doesn't look like a continuous function at all. It's bouncing all around. You have all these different directions. It's changing a lot from K to K. It's not interpolating something nice and continuous. But if you have that these processes themselves form a stochastic process, maybe they're sort of IID samples from something, and they start to average out. So they will themselves simplify as you run this process over larger amounts of time. And that's something which often goes by the name homogenization. The classic example is that you do random walk on a random object. So this is a picture of Z2 bond percolation. You take infinite Z2 lattice and you randomly throw out some of the edges, and then you do random walk on it. And what you end up seeing is that it behaves like Brownian motion as you zoom out. But I mean, there's some obvious flaws because there's holes missing where the graph has been deleted, and there's other sorts of distortions which are occurring. Now it still ends up becoming Brownian motion as you zoom out. On a mathematical level, you actually have to change the type of statement you end up proving. So for example, it's not true that the transition function is in supremum becoming close to the normal transition function. Look, there's holes and stuff like that. So you have to modify the mathematical statement you prove when you make the comparison of the random walk and the Brownian motion. But you can still do it. You can still do something. Okay, so that leads me to introduce homogenized SGD. So this is a process which you can take as a high dimensional equivalent of SGD, and I'll formalize the statement in a second. It is a stochastic differential equation. It has a mean term. And the mean term, well, this F was the objective function that I was minimizing. So this is the full least squares problem with a L2 regularizer. And this is the empirical risk. So it's just this, but dropping the regularizer. And I just want to say a few things about it. So, so this is truly the conditional mean of SGD. In mean, SGD behaves like small steps of a full gradient update. This covariance function is not actually the covariance of the increments of SGD. It's something else. I've done something to it. I've simplified it somehow. And that's an important simplification. So what is this diffusion coefficient? So in my least squares problem, I take 2 over n times the empirical risk times the Hessian. So this is just A transpose A. So I can write it out. It's this is just expanding the empirical risks, the sum of I equals 1 up to n of these things squared, and then this is the outer product. This is A transpose A. The actual increment of SGD's covariance is this thing. So what's the difference between this and this? Well, there's 2 major qualitative differences. First is that this term basically has been just dropped. And the second thing is that I've, let's say, massaged this to be this. What's the main difference? If you like, this is like a expectation of the product of 2 random variables. This is the product of the expectation. So it's a type of decoupling between the actual value, the function values, and the directions of the updates. Okay, so that's the main difference between these 2 things. And I wanted to formulate a theorem to show you what it would look like. It's a lot of assumptions. And what does it say? So first of all, I'm going to delay the main assumption to the next slide. So I need that A and B have some kind of random matrix theory inspired properties. I'm going to say more about those in a second. Second thing, I'm going to do this both for the empirical risk, but I'm going to allow you to put some other observable that you're interested in. So this was related to a question that we had. So empirical risk is not always what you care about. You also want something else. Let's say you want to test the result of your training on something else. So this is, for example, population risk. And for us, we're going to do this for a quadratic. So we're staying very much in the class of quadratics. You know, it'd be interesting to do something for non-quadratics too. There's many, many interesting functions to look at. And we need some sort of bounds on the behavior of that quadratic. I'm going to assume that gamma, which is my step size schedule, is bounded. Now, I'm not going to assume anything about things being convergent. This could be a choice of gammas which are big enough that your iterates are just blowing up and going off to infinity. If that's what you're interested in, great. We can still say that this SGD and homogenized SGD are similar. Part of the reason that's good is that if you want to know about the convergence properties of SGD, which are non-trivial, then you could answer instead the convergence properties of this homogenized SGD. My D and my N, so the matrix A is n by d, parameters of the problem. They should both be big, and they should be related. I want d and n to be like powers of each other. And then finally, if you take any finite time horizon, and I look at the difference between my empirical risk, my population risk at these iterates, and the same of homogenized SGD, the probability that they deviate by a power of the dimension goes to 0, and goes to 0 also like a power of the dimension. And this here can be any desired power, so I lose something. So it's a little bit of an asymptotic statement because I don't quantify what all these constants are. But this probability is basically very high. Okay, so this is all to say that the loss of SGD and homogenized SGD are close, provided that there's some assumptions on A and B. I want to say a little bit about that. So this is the type of assumption that we need. It's formulated for the resolvent matrix. The resolvent matrix is extremely useful in formulating statements about random matrix theory. And I'm going to suppose that on some contour that encloses the eigenvalues of, and here all of my resolvents are for A transpose, that, for example, I take my second term here. If I look at the off-diagonal entries of my resolvent, they're bounded by, this is a negative power of n to some power. This is usually held up as an example of, if you wanted to connect to something more concrete, properties of eigenvectors of the matrix AA transpose. It's essentially like saying that all entries of all eigenvectors of AA transpose are small, entry-wise small. So the eigenvectors are not aligned with any coordinate direction, which would be a problem for the behaviors of SGD if you're making row-wise updates and eigenvectors are aligned with individual rows. This is going to cause exceptional behavior. Likewise, the first assumption is rather, if you take the resolvent, you multiply it by B, then its entries are all small. That's like saying that the rows of the matrix A are in some sense not strongly aligned with your target B. So that individual rows give macroscopic updates in the direction of your target vector. That would be another thing that would cause this homogenized picture, continuous picture to break down. And the third one is something about the on-diagonal parts of the resolvent being close to mean behavior. Okay, so I'm not even showing all the assumptions, but this is the type of assumption that you need. And these types of assumptions are can be checked for matrices A, which have independent rows. That's where you even have a chance of this being true. So independent rows in particular for this, sometimes with non-independent rows. And not even every matrix with independent rows, it should be independent rows and some other good properties. But for example, we had the cases that we checked a Gaussian random features model. We checked some other matrices of the form of random matrix times deterministic matrix. Okay. All right, so I promised to give a way to understand what I said without anything like Brownian motion. And so I can derive for you a deterministic function, which also explains the behavior of the empirical risk and the population risk or some other observable. To explain that, I should also say, why is homogenized SGD? Why should you even care? So I made a big deal about this this coefficient not being the same thing that you would actually get if you computed the correlations in SGD. And this diffusion coefficient is quite simple for the following reason. So, well, first of all, the Hessian in this case is just A transpose A. It's a fixed matrix. And then you have this L of xt. So it turns out that if you just change the basis here and you work in the basis, the eigenbasis of A transpose A, all of the coordinates in that basis of this coupled family of stochastic processes are almost independent. They're just depending on each other through this one scalar, L of xt. It's the only way in which those coordinates couple at all. But L of xt is the loss of the entire system. If the dimensionality is large, it's reasonable to expect that L of xt concentrates around a deterministic function. Now, if I replace L of xt by a deterministic function, the individual coordinates in the spectral basis of A transpose A are now independent of each other. So I just have a bunch of single variable stochastic differential equations running independently of each other. The only data that I need to supply is what is the behavior of L of xt. So L of xt is going to concentrate, and I can use the idea above to derive this. It's a self-consistent type of operation. It's going to concentrate around the solution of a Volterra integral equation now. And the simplest case that I can show is the constant step size case. This is where things are really nice. So it's going to look very similar to what you saw. You have psi is equal to the empirical risk of a gradient flow now. So before we had momentum gradient descent, now it's an ODE, gradient flow, plus something that corresponds to the noise, to the way in which SGD noise is being solved. And it's just some kernel of t minus s times psi of s. I mentioned this before, I'll say it again quickly. So you can give a heuristic understanding of these two terms is that at a time s, the amount of noise generated by making the estimate of the gradient, which is not the true gradient, is proportional to psi, which is the current empirical risk, current loss. And then that is going to be solved by the mean dynamics of the gradient flow. And so it gets sent to 0. And if you keep track of the progress, it's just this k of t minus s function. So all of this is in high dimensions. All of these noises that you're creating are completely orthogonal to each other, for which reason there's no interaction between any of them. So you just end up with an integral over all of the noise generated over the lifetime of the algorithm times the rate at which it's getting sent back to 0. By the way, this was to me very exciting. This is the renewal equation from probability theory from stochastic processes. This is the thing like your light bulb burns out and you're waiting until you have to replace the light bulb. And there's a function of the lifetime of a light bulb. The renewal equation tells you it's an equation to derive the tail function of how long you have to wait for your next light bulb burnout. Anyway, it appears here in a completely different context. This is the renewal equation. Let's see, how am I doing on time? I have 10 minutes, 10 minutes. There's a lot on this slide. I thought I would just show how this updates in two ways. So I want to just carve out two facts from this slide. So first of all, the slide before was for constant step size SGD. You can do variable step size SGD. The formulas aren't as nice. So instead of convolution equations, you have to keep track of the integrated amount of a step that you've taken, so gamma, which is the integral of gamma of s. And then the equation you saw before just becomes now this one. So it's the same, except for gammas are being replaced all over the place. The second thing, which was not covered, was that if you took your external observable. You want to test, you test the performance of your state, some other problem, so your population risk. It kind of piggybacks on top of the other one. So this is not a Volterra integral equation. Rather, you just take the output of what the empirical risk one is doing. You solve what the mean behavior of your population risk is doing, and then you just add some extra term to get the behavior of some other observer. So in the end, this is the formulation of the statement. So if you take your empirical risk of homogenized SGD and your population risk of homogenized G, they're connected to these two functions, psi and omega. The other thing is I tried to call this a solvable model. I don't know if anyone noticed this, but solvable I guess means different things to different people. I call this solvable. It's a single. There's no dimension parameter here. There's no like solution of this by elementary functions. So it's not solvable in that sense. It's not just an exponential or something like that. But this type of object can be solved efficiently numerically. First of all, it's solved by Picard iteration. And in the convolution case, you could even use clever versions of Picard iteration, like fast Fourier transform techniques, and really get it going. The other way in which this is solvable, again, especially in the convolution case, is you can give very, very precise and directly out of a textbook asymptotic behavior of solutions of convolution Volterra equations. So if you want to know how psi of t behaves as t goes to infinity, especially in the convolution case, there's a closed Laplace transform formula for the solution of a convolution Volterra equation, and you can extract all sorts of behavior about the convergence. As an example of one simple application, and in time allowing, I'll say more about it. If you want to know the convergence threshold, when is your algorithm convergence? I mean, one of the biggest problems with this type of optimization is that you have these parameters and you have to go figure out the parameters. And it's nobody tells you what to do, and well, people tell you what to do, and it doesn't have anything to do with what you're doing. So you then have to go figure it out. What are the choices of parameters? And in this setting, you can compute the exact convergence threshold for this algorithm. And it has to do, for a convolution Volterra equation, with the norm of this K. And the norm is the L1 norm of the K. So if you compute the L1 norm of the K, it turns out you can do it in closed form. It's something to do with some trace. So gamma over 2n times the trace of something involving the Hessian. That should be less than 1. If that's less than 1, then the algorithm is convergent. It's if and only if. So it's bigger than 1, it's going to go up to infinity. Okay. So there's some advantages to this. I would just make some conclusions. So what have I done? So I showed you homogenized SGD, which allows you to compare to a Volterra equation. And Courtney showed this. I showed this slide. So this is an actual illustration of such a setup. So I wanted to say a few words about the picture. So this is a simple classification modeled least squares setup. We take this image data set, CFAR 5M, which was CFAR 10, but then it was boosted up to 5 million images using some sort of magic generative model. And then we trained the car boat classification problem on it, and we did a random features regression. So this is the empirical risk of the actual norm of the residual and the least squares problem that you're running. Okay, the algorithm is random. The Volterra is deterministic. So it captures the eventual mean behavior of the loss. We also show the population risk. So this is if you take another set of pictures and now test the output of your training, how well do you classify your car boat situation? Of course, it's quite noisy. So the actual Volterra behavior seems like it's getting lost. We smoothed it out a little bit. So that's if you just take a moving time average of the risks, and just so that even that's a little bit hard to see if you just, sorry, the axes are changing every time. If you just plot the Volterra equations, this is what you end up seeing for the actual population risk. So this theory gives you a way to compute these lines. That's the conclusion to draw from this. There is a way to compute these lines. What is there to learn from it? So, one example, something that you could take home, and don't have a lot of time, so I'm not going to fully explain myself, but in a statistical setting, if you do the setup that I had and you want to test the behavior of constant step size SGD, you want to formulate what is the excess population risk. So if you run SGD and you run it to stabilization, I'm going to say stabilization, it doesn't converge to something. You don't end up interpolating the problem. So you run it to stabilization. You have some state, and you take your guess for what the solution of AX minus B is, and you go and test it. It's not one of the classic estimators. It's not the minimal norm estimator. It's some estimator that gets produced by constant step size SGD. And you can test the performance of it on your extra problem. So you have some other test problem and you want to stick your input from your estimator in there and see what the performance of it is. And it ends up producing an estimate with a worse performance. It has a higher risk. The additional risk is this quantity, this excess risk. So psi infinity is actually the limiting training loss from the problem. So you run this statistical problem, and your training is stabilizing at some level. If it doesn't go to zero, then you have a non-zero excess risk. It appears in the form of psi infinity times some gamma over 2n. A is the actual data matrix. Sigma is the covariance matrix of the actual population data. So if this is, if these are positive, then you do have some excess risk by doing this. On the other hand, if these are small, if psi infinity is small, and that would typically be the case, that could be down by orders of thousands or tens of thousands from where you started, then it's probably not worth bothering. There's some other features which may be interesting, like the actual shape of this term is somewhat interesting in the sense that there's the L2 regularization parameter appears here. So this A transpose A over A transpose A plus delta I is something like a projection, a soft projection operator in the direction of the big eigenvalues of A. And so it's only those parts which end up contributing to the limiting excess risk. And the other thing is that you can get rates. I think Courtney actually talked a fair bit about this, but there's a totally parallel story here. As you increase the step size gamma, the rates of convergence have a regime where they go through just proportionate increase. That is, the rate of convergence just scales like gamma. You go bigger and bigger gamma, everything's honky-dory. You just double the gamma twice as fast. And then at some point that stops, as it has to. And you can characterize this line. It has to do with when your convolution Volterra equation there's an eigenvalue problem associated to a convolution Volterra equation called the Malthusian exponent problem. And this Malthusian exponent characterizes this experiment. And then, of course, if you keep going, it's just going to go off to infinity. Okay, so I'll stop there. This is just another picture of similar type of thing. This is MNIST's digit classification, and well, I ran the training and expected risk, and those are the Volterra lines. Okay, thank you. Yes, please.